Picture this, a universe so young, so raw, that not a single star has yet flickered to life. Complete darkness stretches across existence, broken only by the fading glow of creation itself. This was the cosmic dawn era, the universe's first chapter, written between 50 million and 1 billion years after the Big Bang. But here's the thing, we're still deciphering that cosmic manuscript, and what we've uncovered so far is rewriting everything we thought we knew. Why does this matter? Because hidden in that ancient darkness are clues to how everything, yes, everything, including you, came to be. The first stars, the first galaxies, even the first whispers of light piercing the void, they all hold secrets that defy our current understanding of physics, time, and reality itself. And that's exactly what we're diving into today. 25 jaw-dropping mysteries from the cosmic dawn era that have left scientists scratching their heads. From stars so massive they shouldn't exist, to black holes appearing far too early, to an entire universe that somehow went from opaque to transparent in what feels like a cosmic blink. So buckle up, by the end of this journey you'll see the night sky differently, because what happened back then is still shaping the universe right now. And who knows, the answer to one of these mysteries might just change our understanding of existence forever, ready to unravel the universe's oldest cold case. Let's begin. Now, let's turn our gaze to the very first stars that ever ignited in the cosmos. Population 3 stars. These weren't just any stars. Imagine celestial behemoths, each one 100 to 1,000 times more massive than our Sun, burning furiously in the darkness of a brand new universe. They were the pioneers, the first to transform the primordial soup of hydrogen and helium into something more. But here's the catch, we've never actually seen one. Why? Because these titans lived fast and died young, exploding in spectacular supernova long before even the earliest galaxies took shape. Their light is so ancient, so stretched by the expansion of the universe, that it's practically invisible to our current telescopes. But their legacy isn't lost. When these stars died, they didn't just vanish, they scattered the first heavy elements across the cosmos, seeding the universe with the building blocks for everything that followed, including planets, life, and even us. So how do we find them? That's where the James Webb Space Telescope comes in. With its unprecedented sensitivity to infrared light, Webb might finally catch the faint echoes of these cosmic giants, either in the chemical fingerprints they left behind or in the rare, distant pockets of the universe where their light is still traveling toward us. If we succeed, it would be like uncovering the very first page of the universe's story. And who knows, what we learn could rewrite our understanding of how stars and everything else came to be. But that's just the beginning, because these stars didn't just fade away, they set the stage for the next great cosmic mystery. Now, let's piece together the cosmic detective work that might finally reveal these elusive first stars. Since we can't observe population 3 stars directly, astronomers have become cosmic archaeologists, hunting for their fingerprints in the universe's oldest light and matter. One key clue lies in ancient quasars, bright beacons powered by supermassive black holes. By analyzing the light from these distant objects, scientists have spotted unusual chemical signatures, like an absence of heavy elements, which could only come from the pristine environment where population 3 stars once burned. But there's another ingenious method: gravitational lensing. When massive objects like galaxy clusters bend light from even more distant sources, they act like natural telescopes, magnifying faint signals we'd otherwise miss. This technique has already uncovered potential candidates for second-generation stars, ones that may have formed from the ashes of their population 3 ancestors. Then there's the fascinating dark star hypothesis. Some theorists suggest that the first stars might not have shone with conventional starlight at all. Instead, they could have been fueled by dark matter annihilation, glowing dimly but lasting far longer than ordinary stars. recent observations have flagged a handful of mysterious objects that fit this eerie profile: cosmic ghosts lingering in the early universe. Each of these discoveries brings us closer to solving the puzzle of the first stars. Whether through chemical traces, gravitational mirages, or shadowy anomalies, we're slowly assembling the evidence that could rewrite the opening chapters of cosmic history. And with every new clue, we're reminded, the universe's earliest secrets are still out there, waiting to be uncovered. Now, let's turn our attention to one of the most dramatic transformations in cosmic history. The moment the universe went from a dense, foggy darkness to the transparent expanse we know today. This pivotal shift, called reionization, marks the era when the first light began piercing through the cosmic gloom, but how it happened remains one of the greatest puzzles of the cosmic dawn. For hundreds of millions of years after the Big Bang, the universe was filled with a thick soup of neutral hydrogen gas, absorbing starlight and keeping everything shrouded in darkness. Then something ionized this gas, stripping electrons from hydrogen atoms and clearing the fog. But what was the driving force behind this cosmic cleanup? The debate splits astronomers into two camps. Some argue that blazing quasars powered by voracious supermassive black holes were the primary ionizers, flooding the universe with intense ultraviolet radiation. Others point to the collective might of countless early galaxies, their young stars pumping out enough energy to do the job. Adding to the mystery, different telescopes tell different stories. Observations from the Hubble Space Telescope suggest reionization was mostly complete by the time the universe was around 1 billion years old. Yet, data from the Planck satellite hints at a more drawn-out process, possibly lasting hundreds of millions of years longer. This discrepancy could mean we're missing a key piece of the puzzle, perhaps an unknown population of faint galaxies or an unexpected source of ionizing radiation. The James Webb Space Telescope is now diving into this debate, peering deeper into the early universe than ever before. Its findings could finally reveal whether quasars, galaxies, or something entirely different lifted the veil on the cosmos. One thing's certain: solving the reionization puzzle won't just tell us how the universe became transparent. It'll rewrite our understanding of how light first conquered the darkness. But here's where things get even more puzzling. As we peer deeper into the cosmic dawn, astronomers are facing a glaring mismatch between what theory predicts and what telescopes actually see, especially when it comes to dwarf galaxies. According to our leading model of cosmology, known as the lambda-cold dark matter model, the early universe should be teeming with countless small, faint dwarf galaxies. These cosmic minnows, thought to be the building blocks of larger galaxies like our Milky Way, were expected to dominate the infant cosmos. Yet, when the James Webb Space Telescope trained its infrared eyes on these ancient epochs, it found far fewer of these tiny galaxies than anyone anticipated. It's as if someone erased half the cast of a cosmic play before the curtain even rose. This missing dwarf galaxy crisis has sent researchers scrambling for answers. Could our understanding of dark matter be incomplete? Some propose exotic forms of dark matter that behave differently, perhaps interacting with itself or ordinary matter in ways we haven't accounted for. Others suggest that early star formation was far more efficient than we thought, with small galaxies burning through their gas so quickly that they faded from view before JWST could spot them. There's even a wilder possibility that some of these dwarfs were never there to begin with. Alternative theories of gravity, like modified Newtonian dynamics, challenge the need for dark matter entirely, though they come with their own set of complications. Whatever the solution, this discrepancy isn't just a minor hiccup. It strikes at the heart of how we think galaxies form and evolve. If the lambda-cold dark matter model is correct, we may need to rethink how stars ignite in these tiny systems. If it's wrong, we could be on the verge of a cosmological revolution. The hunt for these elusive dwarfs continues, with JWST sifting through the faintest glimmers of the early universe. Every new observation brings us closer to solving this cosmic whodunit, and perhaps rewriting the rules of galaxy formation in the process. Now, shifting our gaze to another cosmic conundrum, we encounter galaxies that seem to defy the very laws of the early universe. Meet Glass Z13, a galaxy so massive and mature that it shouldn't exist, at least, not according to our current understanding of cosmic evolution. Discovered by the James Webb Space Telescope, this ancient behemoth appears fully formed when the universe was a mere 300 million years old, a cosmic toddler by universal standards. What makes Glass Z13 and others like it so baffling is their sheer size and complexity. These galaxies boast billions of stars, intricate structures, and even dust ingredients that, in theory, should take much longer to assemble. Imagine finding a skyscraper in the middle of a prehistoric jungle. It's that level of improbability. Astronomers have dubbed them universe breakers because they don't just stretch our models, they threaten to snap them entirely. The heart of the problem lies in the timeline. According to prevailing theories, galaxies grow gradually, starting as small clumps of gas and dark matter that slowly accumulate stars over billions of years. But Glass Z13 and its peers suggest a different story, one where galaxies grew at breakneck speeds, achieving maturity in a fraction of the expected time. This raises urgent questions. Did star formation in the early universe operate under different rules? Could supermassive black holes have turbocharged galaxy growth? Or is there a fundamental flaw in how we measure cosmic ages? Some theorists speculate that dark matter may have clumped more efficiently in the early universe, creating gravitational wells that funneled gas into galaxies at unprecedented rates. Others wonder if our assumptions about the Big Bang's aftermath need revisiting. Whatever the explanation, these cosmic outliers are forcing us to rethink the playbook of galaxy formation. As JWST continues to uncover more of these impossible galaxies, each discovery chips away at our confidence in the standard cosmological narrative. Are we witnessing the birth of a new paradigm, or merely the growing pains of a deeper understanding? One thing is certain: the early universe is far stranger and far more inventive than we ever imagined. Now, let's tune into one of the most puzzling silences in cosmic history, the mysterious radio hush of the cosmic dark ages. Despite being packed with hydrogen, the universe's most abundant element, this era left behind almost no detectable radio signals. It's like having a room full of people, yet hearing nothing but static. The key to unlocking this mystery lies in something called the 21-centimeter forest. Picture the early universe as a vast cosmic jungle with hydrogen gas acting like trees. As light from the first stars and galaxies traveled through this jungle, it interacted with the hydrogen, leaving faint imprints like shadows at a specific radio wavelength of 21 centimeters. These imprints could reveal how the universe evolved from darkness to light, but detecting them is like trying to hear a whisper in a hurricane. Then came EDGES, a groundbreaking experiment that claimed to pick up a bizarre signal at 78 megahertz, a frequency that shouldn't exist if our current models are correct. This signal, if real, suggests the early universe was far colder than we thought, or that dark matter might have interacted with ordinary matter in ways we never imagined. Either scenario would force us to rewrite cosmic history. Skeptics argue the signal could be interference from Earth or instrument errors, but if confirmed, it would be the first direct glimpse into the cosmic dark ages. Imagine discovering a hidden chapter in a book you thought you knew by heart. That's the potential of EDGES, a tantalizing clue that might finally explain why the universe stayed silent for so long. As radio telescopes grow more sensitive, we're inching closer to decoding this cosmic quiet. Will we uncover new physics, or will the silence deepen the mystery? Either way, the dark ages are proving to be anything but dull. Now, let's turn our attention to one of the most intriguing cosmic riddles, the enigma of primordial black holes. These mysterious objects, born in the chaotic aftermath of the Big Bang, might hold the key to unlocking the secrets of dark matter. Unlike the black holes we know today, formed from collapsing stars, primordial black holes could have emerged from the extreme density fluctuations in the universe's earliest moments. Imagine a universe so dense that pockets of matter collapsed under their own gravity, creating black holes as light as an asteroid or as massive as 1,000 suns. If these objects exist in vast numbers, they could make up the invisible dark matter that shapes galaxies yet eludes detection. The idea is tantalizing. What if the missing mass of the universe has been hiding in plain sight as countless tiny black holes? Primordial black holes might also explain another puzzle, the rapid formation of early galaxies. Their gravitational pull could have acted as cosmic seeds, gathering gas and dust to spark star formation faster than current models predict. Recent observations of unexpectedly mature galaxies in the cosmic dawn era fit this scenario, suggesting these ancient black holes played a role in building the universe's first structures. But here's the catch: finding them is incredibly tough. Black holes this small don't emit detectable radiation unless they're actively feeding, and even then, they're easy to miss. Some theories suggest they could reveal themselves through subtle distortions in starlight or rare bursts of radiation as they evaporate. Others propose that networks of gravitational wave detectors might one day catch the faint ripples from their collisions. The wildest part, we can't even rule out the possibility that asteroid mass black holes are drifting through our solar system right now, invisible yet ever present. If future telescopes or experiments confirm their existence, it would revolutionize our understanding of dark matter and cosmic history. Until then, the primordial black hole enigma remains one of the most thrilling unsolved mysteries of the cosmic dawn. Next, we'll delve into another cosmic contradiction, the baffling case of the missing lithium, where the universe's chemistry doesn't add up as predicted. Now, shifting our cosmic lens to another puzzling anomaly, we encounter the lithium discrepancy, a mystery hiding in plain sight within the universe's oldest stars. According to the Big Bang's playbook, the early universe should have produced precise amounts of light elements like hydrogen, helium, and lithium during nucleosynthesis. Yet when astronomers measure lithium levels in ancient stellar atmospheres, they find only about 1/3 of what theory predicts. Where did the rest go? This isn't just a minor accounting error. Lithium-7, the isotope in question, acts like a cosmic receipt from the universe's first few minutes. The shortfall challenges our understanding of both particle physics and stellar evolution. Some theories suggest these pioneer stars might have destroyed lithium in their nuclear furnaces, though models struggle to explain how without altering other observed element ratios. Others propose more exotic solutions. Perhaps unknown particles interacted with primordial matter, or gravity behaved differently in the ultra-dense early universe, skewing nucleosynthesis. The plot thickens when we consider where the missing lithium might be hiding. Could it have sunk into stellar cores, invisible to our telescopes, or does it linger in diffuse gas clouds between galaxies, eluding detection? Intriguingly, some measurements of the interstellar medium show slightly higher lithium levels, hinting at a redistribution over cosmic time. What makes this enigma so compelling is its stakes. If standard nucleosynthesis calculations are off, it could imply gaps in our knowledge of fundamental physics. Alternatively, if stellar processes are responsible, we might need to rewrite the life cycles of the universe's first stars. Upcoming telescopes like the Extremely Large Telescope could settle the debate by analyzing lithium in even older stellar populations. Until then, this elemental mismatch remains a quiet but profound reminder that the cosmic dawn still holds chemistry secrets waiting to be decoded. Next, we'll explore the colossal hydrogen clouds known as Lyman-alpha blob structures so vast they defy easy explanation. Now, let's turn our attention to one of the most visually striking mysteries of the cosmic dawn, the enigmatic Lyman-alpha blobs. These colossal clouds of hydrogen gas stretch across thousands of light years, glowing faintly in the ultraviolet light emitted by young, energetic stars. But what exactly are these gigantic structures, and why do they defy our expectations? One leading theory suggests these blobs could be protoclusters, vast nurseries where dozens of galaxies are forming, their collective starlight illuminating the surrounding gas. Imagine a cosmic metropolis under construction with the glow of countless young stars lighting up the neighborhood, yet not all blobs fit this picture. Some appear isolated, lacking the dense galaxy clusters we'd expect to see. Another possibility is that these blobs are the result of galactic winds, powerful outflows from intense star formation or supermassive black holes. Picture a galaxy blowing massive bubbles of gas into space, like a candle flickering in the cosmic breeze. These winds could carry gas far beyond the galaxy itself, creating the vast, glowing structures we observe. Then there's the most intriguing idea of all, that Lyman-alpha blobs might be illuminated filaments of dark matter. According to this theory, dark matter's gravitational pull funnels ordinary hydrogen gas along invisible cosmic highways, lighting up where it's energized by nearby galaxies. If true, these blobs could be our best chance to map the hidden scaffolding of the universe. What makes these blobs so puzzling is their sheer variety. Some are chaotic and turbulent, while others appear smooth and serene. Some sit at the hearts of bustling galactic hubs, while others float in near isolation. This diversity suggests there might not be a single explanation. Instead, Lyman-alpha blobs could represent multiple cosmic phenomena wearing the same luminous disguise. Upcoming observations with next-generation telescopes may finally unravel their secrets. Until then, these glowing giants remain a captivating reminder of how much we still have to learn about the universe's formative years. Next, we'll tackle another missing piece of the cosmic puzzle, the baffling case of the universe's lost matter. Now, shifting our cosmic detective work to another head-scratching mystery, we arrive at the case of the universe's missing matter. Here's the puzzle. When astronomers tally up all the normal matter, the stuff that makes up stars, planets, and you and me, over half of it from the cosmic dawn era is simply nowhere to be found. It's like misplacing the keys to the universe, except these keys make up the very fabric of reality. So where could all this matter be hiding? One leading suspect is something called the warm-hot intergalactic medium, or WIM for short. Picture this: vast, faint webs of superheated gas stretching between galaxies like cosmic spider silk. These filaments are so diffuse and so scorching hot that they're nearly invisible to most telescopes. But when matter falls into these threads, it heats up enough to glow in X-rays, offering faint clues to its whereabouts. The challenge, detecting this elusive WIM, is like trying to spot a single lit match in a foggy forest. That's where fast radio bursts come in, those mysterious milliseconds-long blasts of energy from deep space. As these bursts travel across the universe, they pass through whatever matter lies in their path, leaving subtle fingerprints in their signals. By studying how these bursts are distorted, scientists can map the hidden matter they've traveled through, almost like cosmic sonar, but the plot thickens. Even with these clever techniques, some of the missing matter still refuses to show up. Could it be hiding in even more exotic forms, like ultra-diffuse clouds or rogue planets drifting between stars? Or might our understanding of how matter behaves in the early universe need a fundamental rewrite? What's certain is this: solving the missing baryon problem isn't just about accounting for lost cosmic ingredients. It's about understanding how the universe assembled itself in those first critical epochs. Next, we'll examine another cosmic curveball: how dust, of all things, appeared shockingly early in the universe's story. Turning our attention to another cosmic surprise, let's talk about something seemingly mundane yet utterly baffling: dust. Not the kind under your bed, but the kind floating through galaxies a mere 700 million years after the Big Bang. This shouldn't exist. Dust, after all, is made of heavy elements like carbon and silicon, which take generations of stars to produce. So how did it show up so early in the universe's story? One leading theory points to supernova, the explosive deaths of massive stars. When these giants go out in a blaze of glory, they spew out newly forged elements, including the building blocks of dust. But here's the catch: even the fastest supernova might not be quick enough to explain the dust we're seeing. It's like expecting a single baker to supply an entire city with fresh bread overnight. Then there's another contender: asymptotic giant branch stars. These aging stars puff out dusty envelopes as they near the end of their lives. They're slower than supernova but far more prolific dust factories. The problem: they take hundreds of millions of years to reach this stage, pushing the limits of how early they could have contributed. This leaves us with a tantalizing possibility: maybe we're missing something entirely. Could there be exotic, unknown processes at work in the early universe? Some researchers speculate about rapid dust formation in dense stellar winds or even in the turbulent aftermath of galaxy collisions. Others wonder if the first stars themselves behaved differently, shedding dust in ways modern stars don't. Whatever the answer, this cosmic dust dilemma forces us to rethink how quickly the universe got messy. Next, we'll unravel another twist in the cosmic dawn saga galaxies that seem to defy the laws of cosmic alignment. Now, let's shift our gaze to something even more perplexing: galaxies that seem to be playing by rules we don't yet understand. Imagine tossing a handful of confetti into the air, only to watch it arrange itself into neat, parallel lines. That's the kind of cosmic oddity we're dealing with when we examine the alignment anomaly. Astronomers have spotted early galaxies, some of the universe's first, lining up in vast, coordinated patterns across billions of light years. This shouldn't happen. According to our best models, the infant universe was a chaotic place, with matter scattered randomly by the afterglow of the Big Bang. So why do these galaxies appear to be following some unseen blueprint? One possibility involves primordial magnetic fields, invisible threads woven into the fabric of space itself during the universe's earliest moments. These fields could have gently nudged gas and dust into alignment as galaxies formed, like iron filings organizing around a magnet. But here's the catch: we've never detected magnetic fields strong enough to pull off such a feat. Then there's the quantum angle. Tiny fluctuations in the newborn universe, amplified over eons, might have created subtle biases in how galaxies clustered. Think of it as rolling a dice millions of times and somehow always landing on 6. Statistically bizarre, but not impossible. Some theorists argue these quantum fingerprints could explain the eerie alignments. But the most radical idea: that we're seeing cracks in cosmology's foundational principles. The cosmological principle states that, on large scales, the universe should look the same in every direction. If galaxies are lining up in ways that defy this rule, it might mean our understanding of the cosmos needs a rewrite. Whether it's hidden forces, quantum ghosts, or a cosmic rulebook we've misread, the alignment anomaly reminds us that the early universe still holds mysteries that challenge even our boldest theories. Next, we'll dive into another enigma: dark matter's surprising behavior during the cosmic dawn. Now, let's peel back another layer of the cosmic mystery: dark matter's puzzling behavior during the cosmic dawn. If dark matter is the universe's invisible scaffolding holding galaxies together, why does it seem to play by different rules in the early universe? Recent observations from the James Webb Space Telescope have thrown a curveball. Simulations based on our standard models predict that dark matter should form smooth, fluffy halos around early galaxies. But what we're seeing is far more clumpy and uneven, like a sponge full of unexpected gaps and dense patches. This mismatch has astronomers scratching their heads. One leading theory points to the nature of dark matter itself. Maybe it's not as cold as we thought. The standard model assumes dark matter particles move sluggishly, hence the term cold dark matter. But if some of these particles were slightly warmer, moving faster in the early universe, they might not clump as predictably, creating the irregular patterns we observe. Then there's the radical alternative, modified gravity. What if dark matter doesn't exist at all, and what we're seeing is a sign that gravity itself works differently on cosmic scales? Theories like modified Newtonian dynamics suggest that our understanding of gravity might be incomplete, especially in the faint, diffuse outskirts of early galaxies. While controversial, these ideas gain traction every time observations defy dark matter predictions. But here's the twist: JWST sharp eyes are also spotting tiny, faint galaxies where we expected none. If dark matter's behavior is the culprit, it could mean early galaxies formed in ways we never anticipated, with dark matter acting more like a sculptor than a passive framework. Whether it's tweaking dark matter's properties or rewriting gravity's rules, one thing is clear: the cosmic dawn keeps challenging our cosmic playbook. Up next, we'll unravel how the universe's largest structures, the cosmic web, took shape in this enigmatic era. Now, shifting our gaze to the grand architecture of the cosmos, let's unravel how the universe wove its intricate web of galaxies and voids during the cosmic dawn. Picture the universe not as a random scatter of stars, but as an enormous, delicate network, threads of galaxies strung along filaments with vast empty spaces in between. This is the cosmic web, and its origins hold some of the most profound mysteries of the early universe. So why do these filaments form where they do? The answer lies in the subtle fingerprints of quantum fluctuations from the Big Bang. These tiny ripples in the fabric of spacetime were stretched by cosmic inflation, creating a blueprint for where matter would eventually clump together. Dark matter, acting as the universe's invisible skeleton, first collapsed into these primordial patterns, forming a scaffold of dense knots and connecting threads. But here's the puzzle: why do some regions become bustling highways of galaxies while others remain eerily empty? The real magic happened when ordinary matter, the stuff we're made of, caught up. Drawn by gravity, baryonic gas began flowing along these dark matter filaments, cooling and condensing into the first stars and galaxies. Think of it like dew forming on a spider's web. The structure was already there, but it took time for visible matter to trace its outlines. Yet, even this process isn't as straightforward as it seems. Some filaments glow faintly with hot gas, while others appear nearly empty, leaving astronomers to wonder what shut off star formation in certain strands of the cosmic web. And then there's the mystery of the missing filaments. Simulations predict a dense, interconnected network, but observations reveal gaps and faint tendrils that don't quite match. Could this mean dark matter interacts in ways we haven't accounted for? Or does it hint at unknown forces shaping the web's growth? One thing's certain: the cosmic web isn't just a static relic. It's a dynamic, evolving structure, with galaxies racing along filaments like commuters on a cosmic freeway. Up next, we'll confront one of the most baffling puzzles of the cosmic dawn: how supermassive black holes grew to staggering sizes almost overnight. Now, let's turn our attention to one of the most jaw-dropping enigmas of the cosmic dawn: how supermassive black holes, weighing billions of times the mass of our Sun, appeared almost instantly in cosmic terms. Imagine a newborn universe, barely 700 million years old, yet already hosting monsters so colossal they defy everything we know about black hole growth. The puzzle begins with quasars, these brilliant beacons powered by supermassive black holes gobbling up matter at ferocious rates. We've spotted them shining across the cosmos when the universe was just a toddler, raising the obvious question: how did they get so big, so fast? Traditional black hole formation starts with the death of massive stars, leaving behind stellar mass black holes that grow over time. But here's the catch: even if these black holes feasted non-stop, they'd hit a speed limit called the Eddington limit, which caps how fast they can devour material without blowing away their own food supply. To reach billion solar mass sizes so early, they'd need to break every rule in the book. This has led scientists to propose a wild alternative: direct collapse black holes. Picture vast clouds of pristine gas, untouched by heavy elements, collapsing directly into black holes without ever forming stars. These cosmic shortcuts could birth black holes thousands of times more massive than stellar remnants, giving them a head start in the race to supermassive status. But even this theory has hurdles. Why don't we see more of these middleweight black holes today? And how did they gather enough gas to grow without triggering star formation first? Then there's the stellar seed camp, arguing that early black holes might have grown faster than we thought, perhaps by feasting in dense, chaotic environments or merging at breakneck speeds. Some even suggest they bypassed the Eddington limit entirely, swallowing gas in violent, irregular bursts. But each explanation comes with its own set of mysteries, leaving astronomers scratching their heads. What's clear is that these ancient giants shouldn't exist by our current understanding, yet there they are, shining from the dawn of time. Their very existence forces us to rethink how black holes grow, how galaxies form, and what extreme physics might be lurking in the universe's earliest moments. Up next, we'll explore another cosmic surprise: pristine gas clouds that somehow avoided contamination from the first stars, offering us a rare glimpse into the untouched ingredients of the early universe. Now, shifting our cosmic lens, we uncover another remarkable relic from the universe's infancy: pristine gas clouds that somehow escaped the chemical pollution of the first stars. These ancient reservoirs of hydrogen and helium, untouched by heavier elements, are like cosmic time capsules, preserving the raw ingredients of the early universe in their original state. What makes these clouds so extraordinary is their defiance of the expected narrative. After the first stars ignited, their explosive death should have scattered metals, astronomers' term for elements heavier than helium, far and wide, contaminating nearly every corner of space. Yet, against all odds, we've detected pockets of gas that remain chemically pristine, as if frozen in time. Their existence challenges our models of how quickly metals spread through the early cosmos and raises tantalizing questions. Did these clouds hide in cosmic voids, sheltered from stellar pollution? Or did they form in regions where star formation mysteriously stalled, leaving their chemistry unchanged? Detecting these elusive clouds is a feat of modern astronomy. Scientists use quasars as cosmic flashlights. When their light passes through a gas cloud, specific wavelengths get absorbed, creating dark lines in the quasar spectrum. The absence of metal absorption lines in these spectra betrays the cloud's pristine nature. Recent breakthroughs with instruments like the Very Large Telescope have spotted such clouds dating back to when the universe was just 1.5 billion years old, offering a rare window into conditions before widespread star formation. Their survival tells a surprising story about the early universe's structure. These clouds likely avoided contamination because they resided in unusually quiet cosmic neighborhoods, far from the bustling star-forming regions. Their isolation suggests the early universe wasn't as uniformly mixed as we once thought, with some regions remaining chemically pristine long after others had transformed. This uneven distribution hints at how slowly metals dispersed in the sparsely populated cosmos, reshaping our understanding of early galactic ecosystems. Yet mysteries remain. Why did some clouds stay metal-free while others nearby didn't? Could dark matter's gravitational pull have shielded them? And how many more might lurk undetected, hiding in the vast intergalactic voids? Each discovery of these cosmic fossils forces us to refine our picture of the universe's chemical evolution. Next, we'll confront another puzzle: why some early dwarf galaxies arrange themselves in perplexing flat planes, defying our expectations of cosmic structure. Now let's turn our attention to a cosmic arrangement that has left astronomers scratching their heads the peculiar way some early dwarf galaxies orbit their larger spiral counterparts. Instead of scattering randomly around their host galaxies as our current models predict, these dwarfs often line up in eerily flat, disk-like planes like planets circling a star. This bizarre phenomenon, known as the satellite plane problem, throws a wrench into our understanding of how galaxies form and evolve. The standard cosmological model, called lambda cold dark matter, suggests that dwarf galaxies should be distributed more or less evenly around their larger hosts, tracing the haphazard paths of dark matter halos. But observations tell a different story. Take the Milky Way and Andromeda, for example. Both have dwarf galaxies clustered in thin, rotating planes, a configuration that's astronomically unlikely if they formed purely through the chaotic mergers predicted by lambda cold dark matter. So why does reality clash with theory? One possible explanation lies in tidal dwarf galaxies, small galaxies born from the debris of violent galactic collisions. Unlike primordial dwarfs, which form in dark matter halos, tidal dwarfs inherit the motion of the gas and stars ripped from their parent galaxies, potentially explaining their aligned orbits. But there's a catch. Tidal dwarfs shouldn't contain much dark matter, while many of these planar satellites do. This inconsistency leaves scientists debating whether we're missing something fundamental about dark matter's role, or if there's an entirely new process at work. Another twist comes from computer simulations. When researchers tweak the parameters to account for certain environmental factors, like the gravitational influence of nearby galaxy clusters, they can sometimes reproduce these flat arrangements, but not consistently. This suggests that either our simulations are still too simplistic, or we're overlooking a key ingredient in the cosmic recipe. Could primordial magnetic fields or large-scale gas flows be shaping these structures? Or does the answer lie in a modification to our theories of gravity? The satellite plane problem isn't just a curiosity, it's a potential clue to deeper cosmic truths. If these alignments defy lambda cold dark matter's predictions, they might hint at new physics governing the early universe. Alternatively, they could reveal unexpected complexities in how galaxies interact. Upcoming telescopes like the Vera Rubin Observatory aim to map more of these systems, offering fresh data to solve the puzzle. Next, we'll delve into another enigmatic force shaping the cosmos, the mysterious origins of magnetic fields in the infant universe. Now, let's unravel another cosmic puzzle, one that's invisible yet shapes the universe in profound ways. We're talking about magnetic fields, those mysterious forces weaving through space, guiding star formation and sculpting galaxies. But here's the twist: no one knows exactly how they first appeared in the infant cosmos. The conventional explanation, dynamo theory, suggests that magnetic fields grow slowly over time. As galaxies rotate, their swirling gas and charged particles act like a giant dynamo, amplifying weak initial fields into the strong ones we see today. But there's a problem. This process takes billions of years, yet we've detected magnetic fields in galaxies that existed when the universe was barely 1 billion years old. How could they have grown so strong so fast? This mismatch has led scientists to consider a radical idea. What if magnetic fields didn't start weak? What if they were born strong, imprinted on the universe during its earliest moments? These so-called primordial magnetic fields could have emerged from phase transitions in the seething plasma of the cosmic dawn, or even from quantum fluctuations in the fabric of spacetime itself. If true, it would mean magnetism isn't just a byproduct of galaxies, it's a fundamental feature of the cosmos, as ancient as light. But proving this isn't easy. Primordial fields would be incredibly faint by now, stretched and diluted by the universe's expansion. To spot them, astronomers hunt for subtle imprints in the cosmic microwave background or look for their influence on the alignment of distant galaxies. Some tantalizing hints have emerged, like unexplained patterns in the light from ancient quasars, but concrete evidence remains elusive. The stakes are high. If primordial fields exist, they could solve not just the early magnetism puzzle, but also explain why galaxies form where they do, or even shed light on dark matter. Upcoming telescopes like the Square Kilometre Array aim to peer deeper into this magnetic mystery, potentially rewriting our understanding of cosmic evolution. Next, we'll explore the molecules that set the stage for the first stars, another hidden chapter in the universe's origin story. Now, let's turn our attention to the building blocks that made the first stars possible, the molecules that quietly shaped the early universe. Before stars could ignite, the cosmos needed a way to cool its gas, and that's where molecular hydrogen and helium hydride entered the stage. These simple yet powerful molecules were the universe's first chemical partnerships, forming in the darkness of the cosmic dawn. Molecular hydrogen, just two hydrogen atoms bound together, played a starring role. As the universe expanded and cooled, this molecule acted like a cosmic refrigerator, allowing gas clouds to shed heat and collapse under gravity. Without it, the first stars might never have formed. But here's the catch: molecular hydrogen is notoriously hard to detect directly. It doesn't emit or absorb light in ways our telescopes easily pick up, leaving astronomers to track its presence through indirect clues like the shadows it casts on distant light sources. Then there's helium hydride, a fragile pairing of helium and a hydrogen ion. Theory predicted it would be the very first molecule, forming when the universe was just 100,000 years old. But proving its existence took decades. The challenge: helium hydride emits light at a specific far-infrared wavelength that Earth's atmosphere blocks, making it invisible to ground-based telescopes. Even ALMA, the Atacama Large Millimeter Array, had to push its limits to spot it in a distant nebula, a breakthrough that finally confirmed a cornerstone of cosmic chemistry. Why does this matter? These molecules weren't just passive spectators. They were the architects of structure, enabling gas to clump and ignite the first stars. Their detection helps us piece together how the universe transitioned from a smooth soup of particles to a tapestry of galaxies. And with every new observation, we're rewriting the recipe for cosmic creation. Next, we'll uncover another surprise: galaxies that burned out before their time, leaving behind cosmic ghosts in the early universe. Now, shifting our gaze to an even more puzzling discovery, we encounter galaxies that seem to have given up on life far too soon. The James Webb Space Telescope has spotted what astronomers call quiescent galaxies, cosmic islands where star formation mysteriously stopped when the universe was barely 700 million years old. These galaxies, full of aging stars but devoid of newborn ones, challenge everything we thought we knew about how galaxies evolve. Why is this so shocking? In the early universe, galaxies were expected to be bustling stellar nurseries, fueled by abundant gas. Finding these dead galaxies so soon after the Big Bang is like stumbling upon a ghost town in what should be a thriving metropolis. Some theories suggest these galaxies burned through their gas too quickly, perhaps due to supermassive black holes heating their surroundings or violent stellar winds blowing away star-forming material. Others wonder if we're seeing them at an odd angle, making them appear dormant when they're actually still active. The implications are profound. If galaxies really did shut down star formation this early, it means the universe had mechanisms to quench them that we don't fully understand. Or worse, our models of galaxy formation might be missing a critical piece of physics. Either way, these cosmic retirees are forcing us to rethink how galaxies live and die. Next, we'll explore whether the first stars preferred solitude or companionship, a question that could reshape our understanding of early planetary systems. Turning our attention to another cosmic puzzle, let's consider whether the universe's first stars were lone wanderers or paired companions. The question of binary star formation in the cosmic dawn era carries surprising weight. these early stellar duos could rewrite the timeline for planet formation and even alter how we search for alien worlds. Current theories suggest the first stars might have formed in pairs more often than we assumed. In today's universe, most massive stars have stellar companions, so why wouldn't the earliest ones follow suit? If true, this means planetary systems could have emerged much earlier than previously thought, even in metal-poor environments where dust and heavy elements were scarce. Imagine planets orbiting twin suns in a nearly pristine universe, worlds bathed in the glow of paired stellar giants. Gravitational wave detectors might hold the key to solving this mystery. When binary stars eventually collide or merge, they send ripples through space-time that instruments like LIGO and future space-based observatories can detect. By analyzing these signals, scientists hope to determine if population 3 stars frequently existed in pairs. A confirmed detection would not only reshape our understanding of early star formation, but also hint at how quickly the first planets could have appeared. The implications stretch even further. If binaries were common, their intense radiation and eventual supernova would have distributed heavy elements differently than single stars, potentially accelerating the chemical enrichment of the early cosmos. This could explain why some galaxies appear more evolved than expected for their age. As we piece together the lives of these ancient stellar pairs, we're not just studying stars, we're uncovering the building blocks of cosmic history itself. Next, we'll measure the light from this era and confront an unsettling discrepancy in the universe's energy budget. Now let's shift our gaze to the faint glow lingering from the cosmic dawn, the extragalactic background light. This ancient afterglow should hold clues about the universe's earliest structures, but something doesn't add up. Measurements reveal a puzzling mismatch between the light we expect and the light we actually detect. Where are the missing photons? One possibility is that our telescopes simply can't see swarms of ultra-faint dwarf galaxies from this era. These dim cosmic fireflies, too feeble for current instruments to spot individually, could collectively contribute to the background glow. If true, the early universe might have been far more crowded with tiny galaxies than our models predict. But there's a wilder alternative, exotic physics at play. Some theorists propose that undiscovered particles, like decaying dark matter, could be absorbing or scattering light in ways we don't yet understand. Imagine an invisible cosmic filter subtly altering the background glow, leaving behind a spectral fingerprint of new physics. This discrepancy isn't just academic. Pinpointing the source of the missing light would help us map the universe's hidden scaffolding, whether it's legions of overlooked galaxies or something far stranger. Future observatories, like the upcoming Nancy Grace Roman Space Telescope, aim to resolve this enigma by peering deeper into the infrared spectrum, where these elusive signals might hide. As we piece together the cosmic dawn's light puzzle, we're not just studying photons, we're hunting for the universe's shadowy architects. Next, we'll venture into the realm of early planetary systems and ask whether worlds could have formed in such a primordial environment. Turning our attention from the cosmic glow to the building blocks of worlds, let's explore an astonishing possibility: planets born from the ashes of the universe's first stars. In these metal-poor environments where heavy elements were rarer than gold dust, planet formation followed rules unlike anything we see today. The first generation of stars left behind a legacy of carbon and oxygen, but little else. This raises a fascinating question: could planets made primarily of carbon compounds like diamonds or graphite have been common in the early cosmos? Imagine entire worlds where mountains gleam like cut gemstones and rivers of tar like hydrocarbons flow across the surface. Astronomers call these hypothetical worlds carbon planets, and they might form when carbon outnumbers oxygen in a protoplanetary disk. In our modern universe, oxygen is far more abundant, leading to silicate-rich planets like Earth. But in the cosmic dawn, the chemistry could have flipped, creating carbon-dominated worlds with exotic geology. The hunt for these relics is challenging. Any surviving first-generation planets would orbit long-dead stars, making them nearly invisible to our telescopes. But there's hope. If such worlds migrated into modern galaxies, future instruments like the extremely large telescope might detect their unique atmospheric signatures. As we ponder these diamond worlds, we're glimpsing a forgotten chapter of cosmic history, one where the very ingredients of planets were fundamentally different. Next, we'll confront a baffling temperature discrepancy that could rewrite our understanding of the early universe's climate. Now, shifting our cosmic lens to another enigma, we encounter a puzzling contradiction in the very fabric of the early universe's climate. Measurements of the cosmic microwave background temperature at extreme distances don't align as neatly as they should. Some observations suggest the ancient cosmos was cooler than our models predict, while others hint it might have been warmer, a discrepancy that leaves scientists scratching their heads. This temperature paradox centers on high redshift observations, where light from the cosmic dawn has stretched into radio waves over billions of years. When astronomers study ancient gas clouds using quasars as backlights, they detect subtle differences in how these clouds absorb energy. The expected fingerprint of the cosmic microwave background, the afterglow of the Big Bang, doesn't always match reality. Could this mismatch point to undiscovered physics? One tantalizing possibility involves dark energy behaving differently in the early universe, subtly altering how temperatures evolved. Alternatively, exotic particles interacting with light might have left an imprint we're only now detecting. Skeptics argue it could simply be systematic errors, imperfections in our instruments, or gaps in how we interpret the data. The stakes are high. If the anomaly is real, it could force us to revise our understanding of cosmic expansion or even the nature of dark matter. Upcoming missions like the Square Kilometre Array aim to settle the debate with unprecedented precision. Until then, this thermal tug-of-war remains one of the cosmic dawn's most provocative unsolved riddles. As we untangle this thermal mystery, our next revelation takes us to the chaotic ballet of early galaxies, where collisions shape the universe in ways we're only beginning to comprehend. Turning our attention to the cosmic dance of destruction and creation, we arrive at one of the most violent yet formative processes in the early universe, the first galactic mergers. Picture two massive clouds of stars, gas, and dark matter, each containing billions of solar masses hurtling toward one another in a gravitational embrace. These collisions weren't just spectacular events, they were the engines that drove the evolution of the cosmos. Current models suggest mergers were far more common in the cosmic dawn than today, with some estimates indicating early galaxies collided up to 10 times more frequently than their modern counterparts. Yet when astronomers compare these predictions with actual observations from telescopes like the James Webb, they find puzzling inconsistencies. Some regions of the early universe show merger rates that align perfectly with simulations, while others appear suspiciously quiet, as if galaxies were avoiding collisions altogether. The stakes of this mystery go beyond mere statistics. Galactic mergers played a crucial role in triggering bursts of star formation, as the violent compression of gas clouds ignited new stellar nurseries. They also fed the growth of supermassive black holes, which feasted on the turbulent inflows of material. But if mergers were less frequent than expected in certain areas, how did these regions still manage to produce such massive galaxies and active black holes so quickly? One leading theory suggests that early galaxies might have grown primarily through steady gas accretion rather than dramatic collisions. Alternatively, our detection methods could be missing faint merger signatures hidden behind thick cosmic dust. Upcoming radio telescopes like the Next Generation Very Large Array aim to peer through these obscuring veils, potentially rewriting our understanding of galactic evolution. As we witness these ancient crashes in slow motion across billions of light years, one truth becomes clear: the early universe was a far more dynamic and chaotic place than we ever imagined. And with that realization, we approach our final cosmic conundrum, the mystery that may tie all others together. Now we reach the grand finale of our cosmic detective story, the mystery of why the cosmic dawn era ended precisely when it did. After hundreds of millions of years of darkness giving way to the first starlight, something shifted dramatically. The universe didn't just continue its gradual awakening, it hit a tipping point, launching into the epoch of reionization. But what flipped the switch? The leading suspect has always been ultraviolet radiation from those first generations of stars and galaxies. As they multiplied, their collective energy began stripping electrons from hydrogen atoms, transforming the cosmos from a foggy soup into the transparent universe we know today. But here's the puzzle. When astronomers calculate how quickly these early light sources could have produced enough radiation, the numbers don't quite add up. The cosmic dawn should have lasted longer based on our current models. Some researchers propose that supermassive black holes played an unexpected role. These voracious monsters, already lurking in young galaxies, may have unleashed powerful jets that supercharged reionization in certain regions. Others point to exotic possibilities like decaying dark matter particles releasing energy, or even primordial black holes evaporating in a final burst of radiation. Perhaps most intriguing is the wild card of cosmic variance, the idea that reionization didn't happen uniformly across the universe. JWST has spotted bizarre bubbles of transparency around some early galaxies, while other regions remained stubbornly opaque. This patchwork pattern suggests local conditions rather than a universal clock, determined when the cosmic dawn ended in different neighborhoods of the cosmos. As we stand at the threshold between these two cosmic epochs, one realization hits hard: the end of the cosmic dawn wasn't just an astronomical event. It was the universe's final act of becoming recognizable to us. Without this transition, light could never have traveled freely across space, and we wouldn't be here to ponder these mysteries. So as our journey through these 25 enigmas concludes, remember, we're not just studying ancient history, we're uncovering the very conditions that made our existence possible. As we wrap up this cosmic journey, let's take a moment to reflect on the most mind-bending mysteries we've uncovered. From the elusive first stars that defied detection to those impossibly massive early galaxies that shouldn't exist, each discovery has rewritten our understanding of the universe's infancy. Who could forget the Great Reionization Puzzle, where the cosmos flipped from opaque to transparent in a cosmic blink? Or those bizarre Lyman-alpha blobs stretching across thousands of light years like celestial ghosts? And let's not overlook the missing baryon problem, where over half the universe's normal matter simply vanished without a trace. But here's the exciting part: we're on the brink of breakthroughs. Next-generation telescopes like LUVOIR, with its unprecedented resolution, and advanced radio arrays poised to detect the faint whispers of the cosmic dark ages, promise to shine new light on these enigmas. Imagine peering even further back in time, perhaps finally catching a glimpse of those mythical population 3 stars, or solving the riddle of primordial black holes. The next decade of astronomy could rewrite the textbooks once again. Before we go, we'd love to hear from you. Which of these 25 mysteries left you the most awestruck? Was it the cosmic alignment anomaly that hints at hidden forces, or those early dead galaxies that stopped forming stars against all odds? Drop your thoughts in the comments. Let's geek out together about the universe's greatest puzzles. If you've enjoyed this deep dive into the cosmic dawn, don't miss out on future cosmic revelations. Hit that subscribe button and ring the notification bell so you're first in line when we uncover the next big space mystery. Until then, keep looking up, because the universe still has plenty of secrets left to share.